What's up, guys? Today we have a quick physics problem that we're going to solve that pertains to the idea of springs and elastic potential energy, and we're looking to solve for K, which is the spring stiffness constant, and the velocity. So without further ado, let's get into the problem. First of all, we'll start by addressing what we are given. We have given the mass of the rocket, which is 0.2 kilograms. It's given that it is 200 grams, which after conversion into SI units of kilograms, that's 0.2 kilograms. Then the displacement of the rocket after it's acted on by the spring is 3 meters, and the how far the spring is compressed, it's given to us as 3 centimeters, of course converted into meters. The correct SI unit for distance, that's 0.03 meters. First of all, let's start solving, and we'll start solving for K, which is the spring stiffness constant, because that will be a good segue into solving for the velocity. So we'll start off by solving for K with the idea that all net forces acting on a spring, if it's in an equilibrium position, should equal 0. And that does give us this graph, or this right here, which is two different forces acting in opposite directions, Kx, which is the stiffness constant, and the displacement acting in an upward direction, and the mass and gravity acting in a downward direction. And those two should cancel out to equal 0. And if we put that into the equation, that will be Kx minus mg equals 0. Then, of course, we're solving for K, so we'll use simple algebra to form this equation right here. K equals mg over x. Then we'll plug in all the values we have. For m, which is mass, we'll plug in 0.2 kilograms. G, which is gravity on Earth, 9.8. And our x, which is displacement, is 0.03. Why 0.03 and not 3? Good question. Because this is spring stiffness constant and it does pertain to the spring, not the object, we'll be using the displacement of the spring. And that will give us a spring stiffness constant of 65.33 Newton meters. Next, we'll solve for the velocity, and we'll solve for the velocity through the equation for conservation of energy. And here, for the conservation of energy, we have two different parts. One part where the rocket has potential energy of spring, and one part where it has potential energy of gravity. And in this case, Ke1, which is the kinetic energy of the side that has potential energy of spring, will be equal to potential energy due to gravity. Why, you may ask? Because when this is acted on by the spring, it will have kinetic energy that will cause the rocket to reach 3 meters of displacement, and that those 3 meters will have a certain kinetic energy, and then the rocket will have, when it's at the 3 meters, it will have the same amount of potential energy as kinetic energy due to gravity.